Welcome back to the BS and Beer Show. BS stands for Building Science. Tonight, we're going to talk about the Kendeda Building at Georgia Tech. Really exciting Living Building Challenge commercial project. So excited to hear more about that. BS and Beer is a grassroots movement. Everybody who is here volunteers their time very kindly to share with us every week. So big thank you to our guests tonight for coming on and talking about this, and our hosts for volunteering their time to make this happen. And a thank you to Fine Home Building and Green Building Advisor for being our media partner, making sure that the show happens every week and that it also gets up on YouTube as a replay for anybody who misses out on the show. Introduce yourself in the chat box. Tell us what you're drinking. Otherwise, people don't know you're here. And we, other than the people on the screen, your friends don't know you're here if you don't tell them you're here in the chat box. So put your questions in the chat box as well. As we go through the presentation, we'll try to get to questions and discussions towards the end of the show. The chat box, if you're new to Zoom, I don't know what you've been doing for the last year and a half. But if you're new to Zoom, the chat box is on the bottom. It's probably already lighting up. Make sure that you pick all panelists and all attendees so that your chats go through to everybody who's also in the audience. Fine Home Building sends out a Zoom reminder every week. If you want to know what the next show is going to be, pop over to the bsandbeershow.com and get on our mailing list. We also periodically send out surveys to hear what people want to see us present on the show or what kind of discussions you'd like to have. So join our mailing list. We also have an audio only version of the BS and Beer Show that's available on Spotify and Apple Podcasts. And last, we'll put up a couple of links in the chat box to associated things, but you might have heard that we're writing a pretty good house book. If we are looking for case studies still, and I actually want to highlight that we're looking for some renovation projects. So anybody who's done a pretty good renovation and wants to submit a renovation project, we'll share the link in the chat box. So submit your projects from all over the country, everything from just a little bit better than code all the way to passive house. We're taking any entries that you guys want to submit for possible inclusion in the book. All right, Ben, do you want to introduce our guests?
Sure. Well, first I'll start off with this evening I'm drinking. I managed to be in the right place at the right time a week ago and scored a 4-pack of Heady Toppers in Connecticut, which is a rarity. So this is my libation for the evening. And we'll jump right into introduction of our two guests. First off, my friend, longtime online compatriot, Bob Kovacs is Vice President of Pre-Construction for Evans General Contractors based in Alpharetta, Georgia. Bob has been heavily involved in trying to address the skilled trades shortage, including teaching residential and commercial construction courses at a local technical college and judging the Teamworks competition for Skills USA. Welcome, Bob. What are you drinking?
Tonight, as usual, Diet Coke, because I'm at the office and I'm going to have to drive home. Tonight's Diet Coke is sponsored by Racetrack, because that's what's conveniently across the street from the office.
Beautiful. All right. Jimmy Mitchell started with Skanska in 2005 and is one of Georgia's first lead managers. He created the Atlanta Mission Urban Garden, and he is a founding board member of the Life Cycle Building Center, a nonprofit based in Atlanta. Good evening, Jimmy. Welcome. And what are you drinking?
Thanks, Ben. I'm up here in actually Western New York right now on 4th of July, and I am drinking a beer from Genesee, which is a Kolsch.
Beautiful. I think, Jimmy, you have a presentation you're going to launch for us, and we'll go a little bit into what this whole Kendeda project is about.
I do. Let me share my screen.
Jimmy, do we want to start with a brief description of what the Living Building Challenge is for some of the folks who may not be fully familiar with it?
Yeah, I do. So, so first of all, the Kendeda Building. This is a finished photo here, and it is we built it at Georgia Tech. It's one of the world's most sustainable buildings, and so Bob and I got to work on it. I had the honor of being able to work on it from start to finish. So love talking about this project and trying to spread all the stuff that's been accomplished here. The big thing about it is it did the full certification of the Living Building Challenge. But before we get there, the Kendeda Building was gifted to Georgia Tech by the Kendeda Fund, and so they, right kind of in these early phases, these Living Building Challenge projects, a lot of foundations support them. And this Kendeda fund, they don't typically invest in capital things like buildings, but with this program of the Living Building Challenge, they wanted to invest at Georgia Tech's campus, and with the kind of the purpose of being what they say a boulder in the lake, of showing folks what design and construction can be like, in particular in the Southeast where it's hot and humid, but where it's just hot and humid and challenging in the Southeast. So if you can do a Living Building Challenge job there, then you kind of do it anywhere. So the Living Building Challenge is the world's most rigorous building certification program, and they go as a metaphor of a flower where it's a program. It's made up of 7 petals and 20 imperatives, but the metaphor of the flower is really that these buildings provide more than they take, and they have a plan, and it's really just kind of a paradigm shift in how a building is thought and how it contributes to the plan as opposed to kind of take. So the 7 petals are listed here, and I have to say they fit some similarities to the LEED programs and whatnot, but the big difference between the Living Building Challenge and other programs is the full certification of the Living Building Challenge is you have to do everything. So all 20 of these imperatives are not optional. And whereas like these other programs like LEED or other certification programs, you might have a menu of options. And okay, if you get to 40 of this, that, and the other, and okay, we can add bike racks or a shower or something, then you can get 1 more credit and then eventually get to your goal. This is everything has to be done. There's no options. It's what we kind of believe is sustainable today, and so it ends up being really interesting because from a design and construction standpoint, everything that you do that is an idea and for an element in the building ends up having positive consequences as well as negative consequences to some of these petals and imperatives of the challenge. And so if anything you do doesn't positively impact 4 or 5 of these petals, then it's probably not going to make it into the building. So anyways, I don't want to get into the nuts and bolts of the 20 imperatives, but there they are, and they're broken up into the 7 petals. And as I kind of tell some of the stories of the building with Bob here, we'll get into how rigorous this is and how interesting this is. So the big concept of the Living Building Challenge is that it gives back more than it takes. And so the three positives of the program are net positive energy, net positive water, and then net positive waste. So, from an energy standpoint, it's actually really easy to understand. One thing that was complex about the LEED program, or still is about some of these other programs, is they'll say, okay, take building code, and you'll get 1 point if you're 15% better than building code, or 20% or 25%. And then, how do you know what code is? And it's different everywhere you go, and it's just really confusing. So one of the great things about this challenge, the Living Building Challenge, it's so easy to understand. For net positive energy, you simply have to generate 5% more electricity than you use. And so that's it. So the discussions become really interesting. We have like a little coffee cart in the building, and somebody said, oh, what if we add an espresso machine? And so it's not just about buying an espresso machine and putting in an outlet and a drain. You also have to add maybe 12 solar panels on the roof, right? And then your structure on the roof isn't big enough, so you have to add another bay of panels, and then it goes on and on and on. And
It's
so,
it's $100,000 coffee cart.
right, it ends up being $100,000 little coffee cart as opposed to just, some espresso. So then, you make the decision, but maybe we go for cold coffee instead of espresso. But, one of the things for achieving this net positive energy is there's 6 things that really impact human comfort in a building, in a space. And you kind of break that up and you think a little bit differently. And, the systems really work together. So of course it's airtight, it's well insulated, and there's multiple mechanical systems throughout that work together to help with comfort and still achieve comfort while using a low amount of energy. So one of the most interesting kind of aspects of the net positive energy is our radiant flooring. So this is a photograph here of PEX tubing that's going into the floor. So what you see here is actually a slab on grade, and this is the first level. It steps up a few times. So this is kind of an image of a couple of the steps. But there's this blue board insulation that's going on top of the slab on grade. And then we have all this PEX tubing on 6-inch centers that are attached to that insulation. And then we're going to pour 3 inches of concrete on top of it. And so that's after the concrete pour, and you can see these the tubing coming out into where the manifolds will be in the walls in the future time. And so basically in the winter time, we will run hot water through the floor and warm up the concrete with the hot water. And then in the summertime, we will run chill water through the floor in the concrete and cool down the concrete. So the primary way that we heat and cool the building is actually through, radiant flooring, heating and cooling. That in concert with ceiling fans and an outdoor air system that keeps the building fresh. The building's so tight that we need an outdoor air system that circulates the air enough to keep it fresh and dehumidified. But they all work together to keep it really energy efficient. And so one of the other things about the challenge is there's a 12-month measurement period. We call it a performance period. So after the building is fully occupied, you have to perform for 12 months and give the data of the meter for the water and the energy and prove it out. And so for our first 12 months, we generated we ended up generating 240% more electricity than we use. The big part of that was COVID for the end part of it. We had a little bit of unutilized months, but then we projected full use and played with the data, and it was well over. It was basically like at 200%, even if it was fully occupied. So the building is essentially exporting energy to campus in the aggregate in the course of the year. So for net positive water, it's a little bit different. It's more like the building has to act as if it doesn't exist, as if it's just woods. And if it were to rain, then the water would go into the groundwater. And so basically, we have to collect water off the solar panels as well. So this image up here is actually the drip edge below a 5 solar panel array. So it's collecting the water and then sending it back to the roof, where then it goes into our cistern. And all the drinking water from the building comes from the rainwater that we treat in the basement. In addition to that, what you're looking at here are these underground pipe R stormwater retention systems. So the water that doesn't get captured into that cistern, we have a volume of it up to a 15-year rain event that can be stored in these pipe R systems that are recycled HDPE pipes. And then that the water will sit there and infiltrate into the aquifer, into the groundwater. And then in addition to that, this is kind of a crazy little image. And you can see value engineering on this photo, but when we use the water, the stuff that we treated from rainwater, you can see my cursor, this is the cistern. So this is a 50,000 gallon cistern inside the building. So then we treat the water right here on the other side of the cistern wall. We have a couple of day tanks, and then we pump the water through the building from here. Once the water gets used, it actually, instead of going to the city sanitary system, it goes to a gray water tank right over here. From there, we actually pump it uphill. So this is maybe one of the more wasteful things, that one little pump. But we pump it uphill to a wetland. This is a water treatment wetland, and it basically flows into the wetland, and there's plants in here that just let nature, eat up anything in that water, and that treats it. And then it overflows into a basin, and then it just flows downhill again back into this series of half chambers. So then all the water that we use for drinking water, it still ends up back into the aquifer after we use it. So there again, the point of the building is it's acting as if we don't exist, and anything that, it's acting like it's woods. And that's where the 15-year rain event, if you end up with a 50-year rain event and it's woods, you're still going to have runoff. So, from an engineering standpoint, that's where they kind of draw the line in the stormwater. So one of the great things that helps us with the water usage.
Great photo. Great photo. I love it.
Yeah. So these are foam toilet for composting. It's, you got to wait like 30 seconds until it foams over, and then you do your business and it slides on through. But basically, every time we use the toilet, it uses this foam and about a tablespoon of water. So, instead of having these 1.6 gallon flushes, we use a tablespoon of water. And so that's the biggest water saver we've got in the building.
When you go into the bathroom stall, there's an instruction sheet on the inside of the door that basically explains to you how to use these toilets, so you don't just go in there and do what you would normally do in a bathroom.
Yeah. Don't drop your cell phone in that one.
No.
Yeah, we'll get them to fish their own cell phone out. So anyways, the one that I'm most excited for, and they mentioned earlier that I helped start this nonprofit in Atlanta called Life Cycle Building Center. It's a nonprofit that's a construction material reuse. So you can donate materials that are reusable, and you can go and shop there, just like Goodwill for clothing, but it's for construction. And so this image here is of the structure. And this is a big item that Bob and I worked on together. And I'll talk about this story. And so a lot of times with the Living Building Challenge, there is a requirement for every 500 square meters of new design space, you have to incorporate a salvage material. And so I wanted to leverage the background of that life cycle nonprofit, and so did Georgia Tech. They gave us this use of this Grinnell warehouse about on campus. It was maybe a mile from the project. And we kind of were able to do like a life cycle at this Georgia Tech warehouse. And so the cool thing about what's brown here is that's all this wood roofing or flooring deck. And the detail is really, really unique. This is the detail on the second level, but this part here is the same everywhere. If I can find my cursor. This is a 2x6, nailed to a 2x4, nailed to a 2x6, nailed to a 2x4, repeated throughout. And so we have our glue laminated columns and beams, and the structural bay between the beams is 10.5 feet. And so the 2x6s that are every other member span the 10.5 feet, and they satisfy the structure. So the structural engineer was good to go with all the 2x6s. And so every other member was allowed to be 2x4s, which gave it this fluted look. It helps a little bit with acoustics, But the really cool thing for the salvage piece is those 2x4s were not structural. And so we set up a, with Lifecycle Building Center, a deal that if any 2x4 that they could scrap, we would buy. And so they got most of their wood. We collected 25,000 linear feet of salvaged 2x4s, primarily from film sets. Georgia has this film industry, and the show 24, we got a lot of wood from. The movie Rampage, we got a lot of wood from, and then some. There's a middle school education seminar thing that we got it from. But anyways, if you can see here, this is a close-up, so it's very pretty when you see it as from a distance, and I'll show you some other photos later.
Yep.
But
The challenge
we
that we had with using those, though, was with all those 2x4s being salvaged and being random lengths, and some of them being twisted and turning and all. There are a number of companies out there that would fabricate these panels if all the material was new. But they said, look, we don't want to take your truckloads of potential garbage, as they called it, and have to cull through it and build a panel and then guarantee that it's structurally sound. So they said, look, we'll build you brand new panels using all new wood. And it was somewhere in the neighborhood of $450,000 for the panels. So we said, well, we can't afford that. Number one. Number two, we have to incorporate this salvaged material. So we came up with a different plan, as Jimmy's about to show you in some pictures here.
Oh yeah, it's awesome. And so Bob and I and our buddy Cale Gasly, we went out to that Grinnell warehouse that I was mentioning earlier, and these were all 12-foot boards of 2x4s and 2x6s that we bought from Home Depot. And so we were like, okay, well, the market wasn't going to give us a fair price to do this. So how bad is it to do? And so then we got a nail gun, and we did it on the floor at this Grinnell warehouse. And it took us 43 minutes and 4.5 seconds to do one 12-foot by 6-foot panel. And that's a photo of the panel that we did on the floor. And then, Bob and I ran the numbers, and we were like, all right, well, if we're going to end up doing 488 panels, was the number, and it would take us like 3 months, and it'd be a crew of so many, and we'd do 8 to 10 a day, and we ultimately, the number that we came up with to do it ourselves and self-perform it was like $800,000 less than what the one, the bids we were getting in the market at the time. So it was a big deal that Bob and I, we put this together and saved on the, from a value engineering perspective.
Yeah, we only built the one of them. That was the extent of my my woodworking that day. We did not, we had other people do the 460 some odd other panels.
This mock-up was not one for in place. It was garbage after.
It was not pretty. and Cale and I just kind of supervised and made Jimmy do all the nailing too. So it was
yeah. So let me show you this. There's this guy, David Luffel, on our team who led it. And then I got to brag about, this is, so I'll show you this slide. This is their Georgia Works group. And so I wanted, there's the equity pedal within the Living Building Challenge. And so in the spirit of the equity pedal, wanted to do a workforce development program. And so there ended up being 489 panels. That was the last one. But we, instead of going out to the carpenter group, there was a Georgia Works as a workforce development program close to a needed area that Georgia Tech had studied. But anyways, we trained 6 of their men to help us. It was about 50 cents more an hour than carpenters, and they were in a program. And so we thought that was great. And so attended some graduations of their program and did that. So those folks are in the construction industry and had a good job on their resume. And I have this video that might mess with our bandwidth. I thought I did anyways.
So while he's looking for that, you can see that the panels actually had to be built upside down. Yeah, you had to build them with the top up because that was the flat part. So they
Can you
just kinda
guys see
stacked
this right
these
now?
pieces. Yeah, it's going.
Okay. Yeah,
So you just stacked it. You put one up, nailed it off, put another piece up, nailed it off. They just, you can see off to the right of the screen there was a steel angle that they used to keep the panels square, and they just ran the far side long, and then after the whole panel was laminated up, they just snapped the chalk line and ran a 16-inch Makita saw down the far end to cut the panel square. They didn't have to be perfect because they were sitting on top of like 6-inch wide beam, so you had a little bit of flexibility in the exact width of it. But so they were, when they got done, they were knocking out about 10 panels a day.
Yeah, and we would try to help them until they hit that figure, because that's what we had figured it at, 8 to 10. And
well, what happened was, we figured it doing it like this, and like I say, just cutting everything, running everything random and then cutting the end off. And one of the guys called and said, when they first started doing it, they said, look, they're only getting like 3 panels a day. So there's no way they can only be getting 3 panels a day. So we went out there, and what we found is they were cutting each piece to length individually on a miter saw and then nailing it all together. So they were wasting all this time, pre-cutting everything. We said, well, where's the 16-inch saw that we had budgeted to cut these things after the fact? You can see it in the video now.
there's David Lovell making the cut.
Yeah. And he says, well, that's a $700 saw. He says, I thought I was saving $700. He said, yeah, but you've doubled the amount of labor hours that that you were using. You pay for that saw in one day, and within a week, they were doing 8 to 10 panels a day instead of 3.
So we had 489 of these panels ready to go, and it was amazing when we went to put them onto the structure. They went on so quickly. It hadn't been done before, so we didn't know how many of these 6 by 10.5 foot panels they could screw in a day. And so we figured, maybe 16 or 20 or something. And the guy was like, oh, I told him, oh, I do a pizza for dinner, and we got to 54 in one day or whatever. So that was really great. So that's one of the salvage stories, and it's the most significant one. And of course, it was the heaviest one. And one thing that I kind of like is we couldn't commingle any of the trash. We had to separate it all out, and I had to know where it was all going. So we did have a few materials that had to go to the landfill, but the weight of the materials that went to the landfill was less than the weight of the materials that we installed that we salvaged from other projects on their way, to the garbage. So, but we essentially, from the net positive waste, we took more from the landfill than we gave to it. Here is the Alumni Association house on the left that's on campus. Was able to talk. They were doing a renovation of the roof because the flashing was leaking. The slate was still nice. So we made these 18 bins and saved all the slate tile. And then we incorporated into the bathroom walls, cut it down to 8 by 2 inch tiles. There was a state of Georgia courthouse being built, and they tore down an archives building, and we salvaged some curbing that went into the hardscape. Tech Tower in 2016 had this renovation, which is Tech Tower is the kind of the iconic building. It's the first building on campus, and they cut in a fire stair and an elevator. And so they were able to save about 70 of these original joists from the 1880s or heart pine. And we made a table out of them and all the monumental stair treads out of them. In fact, when we sanded them down and made the stair treads out of it, we saved the project about $65,000 versus the original design. And they're gorgeous. So the salvage here, like Bob and I said earlier, that salvage wood saved some money. This saved us money. So the salvaging actually saved us money on the project. One thing that was cool when we made those cuts, the majority of the dimension was 10.5 feet, but we had to buy 12-foot 2x6s for the structure. So we had about 10,000 pieces of 2x6 scrap, and we saved it. And then there's these stairs that had to make these small steps, these couple of foot stairs in a few locations. So not the monumental stairs from level 1 and 2 to the basement, But anyways, we made all those stairs out of the kind of like butcher block out of those pieces of 2x6 scrap. There was a tree save program on campus. This is some black oak that was saved. We milled it, we dried it for about 15 months, kiln dried, and then we have quite a lot of bars and counters made out of trees that were storm fallen. So, yeah, the next thing, I have a few value engineering ideas that we went through in the early part of the design phase. And so this is a fun one. One thing that was kind of challenging about the project, it was the first of its kind, and everybody's real excited to be on it. And we really, if there was something we needed to work through and figure out, we did it. So we probably spent too much time figuring out stuff, but it's a great benchmark and case study for the rest of the market. So our mechanical system throughout all the way through the end of design development, which is very late, we had two totally separate systems. One was, they both had the radiant flooring, as I mentioned, but one would use as energy source from the chill water campus loop, and the other one would be from geothermal wells. So because there's this limit of disturbance restriction of the Loon Building Challenge, these wells really needed to be underneath the building. And so we had one that was a 500 foot deep geothermal wells. And ultimately, it lost out to the campus chill water loop because the chill water loop lines went right through here on the neighboring street. So it was super close. It was only about 40 feet away from our chillers. And with the way the chillers work is they create chill water and they have discharged hot water. So for us, that's when we use them in the winter time. The discharge hot water, instead of going to a normal cooling tower system, actually goes through our floors to heat the floors. So in the winter time, we actually are sending chilled water to the chill water plant, giving it energy. Anyways, so it saved about $600,000 to tie into that campus chill water loop, as opposed to doing the geothermal wells. Honestly, we got a great price in the geothermal wells, and if that loop hadn't been so close and convenient, I think it would have won out. But in this case, we ran it through that. This is another good one. The original design had as much glazing as you can kind of think of, and that was on the top. And then, you know, we sat down with the engineer with the light study, and we kept all the foot candles, really still kept it a very glass heavy building, but reduced it significantly. And you can see below, we actually didn't really lose any daylighting at all in the lower, but we saved, you know, probably $250,000 in glazing. And keep in mind, this is all very efficient stuff. So it was triple pane glass, you know, $115 a square foot stuff type thing. So
yeah, and that's something that, you know, you Mainers are used to seeing on pretty much everything that you build now. This triple pane, and you don't see a whole lot of any triple pane glass in Georgia. This is probably the first building down here that's got it, but it was the only way to meet the energy requirements.
Yeah. So this is a good shot of that nail laminated timber ceiling. So anywhere you're in the building and you look up, you see that 2x6, 2x4. But from a structural item, this is a good one that Bob worked on with Uzin and Case, our structural engineer. The original concept had only wood and not this hybrid structure that you see with the steel rods and cables. So these beams were very thick, and maybe that in particular, this, like these guys right here, you know, 42 inches deep. And it was just too much wood. And when we went to the market to look at it, it was just kind of wildly expensive. And so then we just said, hey, we got to get some wood out of it. Not necessarily take wood away, but just how do we be smart about this? And so Uzin and Case came up with this queen post truss. And so we kind of, this support, this steel rod and post support essentially makes up for the depth piece of the beam. So we were able to take up maybe 20 inches to 2 feet out of the depth of these beams across the building. And then what was really nice about this, and this is where I think the team, it was really an integrated team. Lordex Sargent and Miller Hall were the architects, but Lordex Sargent, they both took this as, okay, well, let's make this a design element instead of something to hide. They showcased it, and so these things are symmetrical and they're throughout, and they even carry it into rooms and they show it off with glass and these kinds of things. So, anyways, not only did we remove the depth of that wood and save a whole lot of the wood material, the wood savings was more than the addition of the steel. It also removed about 18 inches of skin on each floor and allowed us to lower that ceiling height, because we could, in this space, this is the middle bay, we don't have a lot of systems running through it, but on the 2 wings on both sides, the ductwork and the conduit kind of run through it, and they're able to run through this interstitial space up here where there formerly was beam, and now it's just the queen post truss. So that, all in all, I think we saved about $500,000 between the savings on the wood and the skin around the building a couple times. So that's our stuff we already talked about. So one thing, so early on I mentioned the challenge, the living building challenge, and we've actually only gotten through about 3 or 4 imperatives so far. The hardest one today is the red list. And so basically, it's kind of like a self-regulated FDA for all the building materials. And there's these chemicals that are known carcinogens or known harmful chemicals, and you just can't have any of them on the project. And so 100% of all the components of the materials have to be disclosed, and then the chemicals that make up those components. And so there is a level of due diligence. So for example, there are like fire protection products that are currently requiring Teflon, and Teflon is one of these red list materials that are not allowed. So yes, we do have Teflon that are in the little sprinkler heads that are part of the fire protection system, but we have to do essentially a research paper to prove out that that's the only option in the market. And then we have to tell at least 3 local suppliers of fire protection, heads that have the Teflon, manufacturers, that they need to do some research and find a way to get Teflon out of their products, right? And so we do that. This is a diagram that shows the complexity of kind of the research paper you've got to do due diligence before you can have something that's on the red list on the building. But we essentially had about 1,200 products, and every single one of them had a research paper on it. That luckily there's this program that if you're a manufacturer and you disclose everything in advance, and you then you can use that Declare program. It's called Declare. It becomes a Declare product, and so with our project, we're the 28th living building. It was just fully certified a couple months ago. We definitely were able to use about 8 to 10 Declare products. But by the end of this project here at Georgia Tech, there were more. Generally, I feel like this is very similar to when we did the low VOC stuff in LEED, where when I first went to the market on that about 16 years ago, the low VOCs, and nobody knew what it was. It took them a few years, about 2 or 3 years. And today, there's an app on your phone. You can go to any, scan a barcode, and they'll tell you what the volatile organic compounds are. And so I feel like with the red list, it can go the same way. And now that we have this comprehensive spreadsheet of all 1,200 products and all the information on the red list from it, other projects in the future can use that. And over time, it'll become easier and easier to find acceptable products. But I mean, it is wild. I mean, to give you a good example, one of them is hexavalent chromium. And so if you guys ever watched that Aaron Brockovich movie, that's the chemical that got into the water there. So when in the galvanizing process, there's typically in the US, there's 2 dips, and the second dip uses this hexavalent chromium chemical. Well, we took this so seriously that the sheet metal, the ductwork in the building, we said, all right, well, let's design the whole thing at the same gauge. And then we calculated if it was all the same gauge, and it would land at it was like 28,000 pounds to 32,000 pounds of ductwork. And you can buy a coil of that gauge at 40,000 pound increments. And they're like, okay, great, that's not too much waste. So we bought a 40,000 pound coil, and we told them to not dip it into the chromium 6 in the galvanizing process. And then we fabricated all of our duct from that coil. And we did stuff like that. You can go through the building with me and point to anything, and everything has a story like that.
It was so crazy that a lot of those connections that you saw in that one picture, there were some pieces, those are all cast steel connections, and there were some areas where they had to do some welding on them, and they used a nickel rod to weld cast material like that, and it was shinier than the kind of dull gray casting material. The architects kind of went, oh, it looks out of place, we got to do something. How can we change the color of that stuff to kind of get it to match more? I said, look, I know I've got some stuff at the house that I use for some of the metal work that you just spray this black magic stuff on it, and it'll turn that thing the exact color you need it. We actually tested it on a piece down in the basement of our office building. We tested it to see if it was going to work, and it was perfect. And the guys brought it out to the field, and they said, we'll just go around and spray this stuff on all these connections, and everything will be wonderful, And somebody went, what's in that bottle? So we had to call the vendor out in California, this company called Sculpt Nouveau, because the back of the bottle says it includes A, B, and C, and other stuff that we're not going to tell you about, basically, because they didn't want to give out their tinting formula. So we called them, and they're like, we're not telling you what's in it. So we couldn't use it because we couldn't prove what was in that that little 1 quart spray bottle. But nobody would have known the difference at the end of the day that it was ever used. But we had to do the right thing and not use it and find another way to get that material the right color.
It was intense.
Yeah.
So on the water system, we will be the first building in Georgia to have our own potable water system, basically, that's not a municipal water system. And so working with the Georgia Environmental Protection Division, we went through the kind of rigor with them. And so the phase 1 of that was to get a water sample of the reservoir. In our case, the reservoir was rain. And so we made a mock-up on the adjacent building, which is a research building. And if there's ever going to be any weird exhausts in the water, it would be from that research building. But anyway, so we put it on that building specifically because there's some fume hoods there and that kind of stuff, and it's right next to it. And so during multiple rain events, this mock-up had the majority of the materials that the water would touch. It had the solar panel, the TPO roof, the roof drain, and the pipe. We had a little filter that was a similar filter. And then we collected rain samples, and then we sent those samples as the reservoir samples to the state. And they were like, yep, this is a good source of water, the rain. And then, the next phase is we built it, and then we had 30 days of testing in the building. And that ended up being a whole rigorous thing. And they are requiring us to put chlorine, but then the Living Building Challenge requires us to take it out. So we actually put in a little chlorine, like a city level. And then we have site use carbon filters that take it out at point of use. So it's all types of fun.
Yeah, even in that picture, you see that roof drain that's on there for that for that mock-up. we called the local plumbing supply house and said, we need a Josem roof drain, that we can use for this, this mock-up. Pop the box open, and these 4 washers that are used to seal the top lid of the, the drain down to the drain body pop out. Like, oh, wonder what those are made out of. And they were, what was it, neoprene that wasn't allowed?
Neoprene. Yeah, it was
the
funny.
washers
We
are
did.
made out of neoprene. You couldn't use them, so we had to call Josem and go, hey, you guys have to ship these roof drains with rubber. They're like, no, we're going to ship them with neoprene. You want rubber washers? Go buy some friggin' rubber washers. So that's the level of detail you had to get into to keep stuff off this red list.
Yeah,
and
and they didn't even have those neoprene washers in the product data. And so when we looked through it and saw it was good, we then saw that it had neoprene washers, and we're like, nope. So we had to change that out.
Yeah, I mean, you had to go to companies like Train. You get a rooftop unit that's got hundreds of components, and the thing shows up on the site, and you have to like literally climb through this unit to make sure that there's nothing in there that's made out of a material that doesn't belong on the job site. So everything had to be brought to the job site months in advance to be vetted to make sure there was nothing on the red list.
So yeah, so the due diligence on that for the mechanical equipment is, there's going to be some insulation and the wiring and stuff that'll have it. But yeah, we basically, we approve it all, review it all, and it was quite a lot of effort. We made a little mock-up for the skin and also for the water collection, the gutter of the panels. And so we had a couple mock-ups on the project. So a couple other things that were interesting. We did blower door test, but we did it before we had the exterior skin on and the interior furring. So we pressurized the building to make sure we didn't have any air leaks. And then we basically pressurized the building, and then we went around filling in holes until it pressurized. And then all those little pieces of tape that had holes on it, we fixed. And then we did another blower door test at the end and passed. So we knew we had a really tight building. As Bob said too, all the red list stuff, we did indoor air quality tests and passed the flying colors. So, there's not a lot of allergens in the building and that kind of stuff. It's really quite fresh. So anyways, the building was 46,870 square feet, but only 37,000 square foot was conditioned. The rest of it was like a rooftop garden that was added. That was actually a nice value engineering add. It was a rooftop garden. And then there's this porch under the PV panels that's also great kind of educational space. The original Kendeda Fund wanted 42,500 square feet, and they were very happy to have this mixture of indoor-outdoor program. If you include that outdoor program, we came in right under $400 a square foot. If you do it just for the outdoor program, the indoor conditioned, then it was just over $500 a square foot. I have to say the site is so nice and costly that it's kind of not totally fair to just use the indoor square footage. It's an expensive site. So it was $18.6 million. So what Shan was going to show, we have, if you go onto Google Maps and you type in Kendeda Building, you can then take this little man here and drop him on one of these little blue bubbles in here. And whoops, let me get this out of the way. And then you can give yourself a tour of the building. So like, right away, these are the stairs that are those salvage 2x6s that are like butcher block. There was a church that came down on campus, and we collected joists out of that church to make these ADA ramps. You can see here how beautiful the 2x4, 2x6s are. This is one of our storm fallen countertops here. That's a black oak. These are the joists from the Tech Tower, that are monumental stair joists. See how pretty they are? And one of the cool little architectural details we did is see if I can get this to work. is on the underneath of them, we didn't sand it. So when you walk, does it go back? No, it doesn't. When you walk underneath the stair treads, you see the original joists unsanded. And then when you walk on them, you see it sanded. Is really cool.
Yeah. Sean's still holding the door open for you, Jimmy. He's letting a lot of air out.
Yeah, that was Sean who was holding the door open for us. So, yeah. Let me go right here.
Yeah, there's fans everywhere in this building. There's something like 100 fans throughout the building because a lot of as Jimmy showed in that first slide early on, they rely on air movement a lot more than they rely on temperature to keep you comfortable. I think the set point in the building originally, it was designed to operate at a set point of like 78 degrees, which for most people is obnoxiously warm, especially down here with the humidity that we normally have. I think. Jimmy, I was talking to Greg Spiro a couple of weeks ago on another job. I think he said they're actually able to operate the building at 74, and everybody's still comfortable because you've got that constant. No matter where you go, there's a fan or more than one fan blowing something on you.
Yeah, I've been amazed at how comfortable it is in there, and it's also been strange. I've gone in there in days in the winter where it's like 18 degrees. And it's totally comfortable. And then I've gone in when it's 100 degrees outside and it's totally comfortable. It seems like the concrete holds a lot of the mass, and then the radiant flooring and the ceiling fans, they're all working together well. This is the manhole to the cistern. So the whole cistern is under here. If we want to go out on level 2, this is the rooftop garden. And there's an apiary back here where the honeybees are. And this is another example of this is not indoor conditioned space. It's that was an outdoor bee box. So, it's a great usable program. We have 4 class labs, 2 large classrooms that sit up like 68 people. We have this large auditorium, which is, over 150, a maker space, an office space for 16 folks on the first floor over here. In the basement, of course, it has the heart of the building, but there's not much program down there other than the fun stuff to see, like the electrical room, the composting toilets.
Yeah, and everything is exposed down there. When you walk down in the basement, there's like one of these screen walls in front of all the equipment. So you can, if you're an energy geek, you can go down there and stare at all of the equipment that's down there. There it is. You can see the switch gear. You can see the composting bins for the toilets. So it's kind of cool. But yeah, the neat thing about this building is it's really probably the first living building challenge project that's actually like a used space, like it serves a function as a classroom. A lot of these buildings they're what I call jewelry boxes. Somebody says, hey, I've got $10 million, go build a living building and name it after me. And it's one of those places that you just walk into and go, wow, this is nice. And it doesn't do anything. Whereas I say this building actually functions as a classroom on day in and day out.
So any questions?
There are lots of questions. I was like, pardon me while I go give myself a tour, because that might be the coolest thing I've seen Google Maps do. So I'm just going to go disappear for like a half an hour. Remind me again, in case you said it earlier, because I can't remember, what is this building for on their campus? So you said classrooms, but does it have a specific purpose?
Yeah, so it's a student commons. So students love to go there and study, and they have classroom spaces. One thing is it really wants to be multidisciplinary space as well. So they're doing things like putting a calculus class in here so everybody has exposure to it, like a prerequisite class. But then also there's going to be the earth sciences, the sustainability oriented classes, design and construction. So the big program spaces, and I formerly served on our civil engineering board, and I know about some of the challenges of the classroom sizes. This is a much needed classroom size. This like over 150 person classroom. So this is a heavily used classroom auditorium space. And then those two 68 person classrooms upstairs over, well, let me go over here, that are up there on the second floor. Those are heavily utilized classrooms as well. This guy, like this guy right in here.
The building doesn't belong to a particular department though, or anything. It's not like this is the civil engineering building or the whatever. So it sees a lot of different uses during the course of a week.
It does. And so like Kim Cobb, who's the climate change embodied carbon specialist, would run a few classes out of here. But then also somebody who's doing engineering ethics might do their class out of here. And there'll be somebody doing calculus, right? I mean, the point is it's a student commons class space where you're just going to take classes.
So we have a question of whether or not you have to trade your shoes in for Birkenstocks when you enter the building.
Yeah, well, it's funny that they kept talking, especially the guy, this Howard Wertheimer, good friend, and he would always talk about, all of us are wearing suits, coat and ties, and but the students just walk around in flip flops and shorts, and so do the faculty. So actually, that's kind of like joked about and encouraged, and that thermal comfort that I showed, it's like your clothing, really should, if this building feels comfortable at that 74 degrees. Especially in the South, it'll be 100 degrees outside and you walk in and it'll be like 64. So we should be able to still like wear our shorts out in the sunshine and then go into a building and not be freezing.
So I guess one of the questions that kind of plays off of that is how do you evaluate a project for health and happiness? And I think we got a taste of how you evaluate a project for equity. How do you evaluate a project for beauty? Like those are all so subjective. What is the framework around that?
You keep Dan Colbert away because that would be a high level of unhappiness.
So the imperatives have what you need to do from a design team standpoint. And those subjective things, I have to say, as a contractor, I kind of trust that the beauty is being accomplished by the design team. And it is here. I mean, it's gorgeous. But there are things like everybody has to have a view of the outside within 35 feet. And when you looked at that auditorium, the design, the original design was actually rotated 90 degrees. Let me come in here. And it was going to go like this instead of like that. And what ended up happening is we did a study of the room, and there was a whole quadrant that was more than 35 feet away from a window. So this, and among other program reasons, we just because of that, we rotated this 90 degrees at design development and totally changed this auditorium specifically for that. And so there's no chair in this building that doesn't have view of the outside within 35 feet. There's other stuff like that with it. But you are right, like beauty. I mean, so for us, of course, the LT panel, when we were talking about the pros and cons, the benefits and the costs, beauty would have been one of the pros.
I guess another thing that kind of came up along that is you had your slide there showing the metrics you guys had to meet, and there was something on there that said scale jumping.
Yeah.
Can you explain what that is a little bit, or can we go back to that slide possibly and talk a little bit about what those factors are?
Yep, absolutely. So Living Building Challenge, of the petals, if you look here at like net positive energy, scale jumping means that if you, if this building, let's say Georgia Tech said we wanted this building to be net positive energy, but we actually have a place on campus nearby where we can put a solar array and meter the amount of electricity we're providing to campus. You could scale jump that and then say, but that has to then be dedicated to the building, right? You can't then, do something else with it. And so that doesn't have to necessarily be on top of the building. In our case, we put it on top of the building. So scale jumping simply means it could be somewhere else. But like the embodied carbon, we basically run a carbon calculation of all the materials on the building, and then we offset it with a carbon credit. So those carbon credits are not on the building site. The equitable investment, if you're not a nonprofit and you're doing this, you have to give a you give a half a point of the whole construction budget to a charity. And that charity, of course, doesn't have to be in the building, so it's a scale jump. So
I had heard somewhere else that you could buy like property in the community and put it into like Open Space Act or something like that to meet those kinds of things.
And in this case, Georgia Tech was a nonprofit, so it wasn't a requirement for them.
So going along with that and some of the scale jumping too is one of the things that popped up in the beginning was the blue board, right? And I think you just said there that you bought carbon credits for some of the stuff that you had to put into the building because it was blue board, maybe fairly carbon intensive. And also there's been a lot of questions about battery storage, right? So you're producing your energy here, but our understanding is that Living Building Challenge requires like a week's worth of storage. So is that something that you could scale jump if you didn't have it on the site too? Oh, well, hey, let's go to the mechanical room. All right, you've got everyone's attention.
So no, so the battery.
Sorry, Jimmy. Let me just say one thing. There is, if you look into the energy system on YouTube, there's a really great kind of tour and walkthrough of some of the infrastructure on YouTube that was done by the Energy Engineering Department of Georgia.
Nice. So our battery system is here. And basically, the way it works for the challenge is the capacity of the battery is calculated, but then that capacity basically has to go to one panel and have the ability to panel that at that capacity for a week. So in our case, it's for resilience. So the panel that our engineers picked were things like the controls and the windows being operable. And it was these passive elements of the building that could still function for a week. But quite often the thing that is the story that's told is like the refrigerators. So then if power went out on campus, you could come to the refrigerators at the Kendeda Building and put your penicillin in the refrigerator or whatnot. So that wasn't actually done here. There's simply just one panel that is energized for the week. And so anything that's on that panel would then go. Of course, that would be separate from the emergency lights. Right here is a battery backup for the emergency lights. And that is separate from the battery backup for that one panel in here.
You can see that, yeah, even without a massive battery storage system, we were still able to, create net positive energy, just given the amount of sunlight that you get down here.
Yeah, and so, basically this is it. This little guy right here, this is the PV array is at DC, and it comes down at 480 volts to this transformer where it goes to AC, and then it comes up here into the switch gear. And so you can read the meter, and basically this is power coming in, but during the day, a ton of power is going out into the grid. And then at night, the power is coming back in. And so, we're generating more than double than what we're using in the course of 12 months.
Is the battery backup for the lighting system run by the solar panel as well, or charged by the solar panel, or is that set? Like,
no, it's
just
separate.
a total.
And if the power grid goes, if the grid goes out, the system is engineered to actually not generate electricity. We don't want to electrocute anybody at Georgia Power thinking that the whole grid's down. So it's strange. If we were like in Alaska off the grid somewhere, it would be engineered differently. But this is grid connected, and so in that scenario, we actually we'll have all those solar panels not being used. Unfortunately, yeah, it's okay.
But you're also not electrocuting people.
We're
So,
also
you
not
know, there's
electrocuting
that.
people.
There
Yeah.
are some people that were involved in that project I might have wanted to, but we did not electrocute anybody.
You got to meet the equity pedal, right?
Yes,
The
I
electrocuted
tried to be
people,
equitable in
at
my,
the same time.
yes.
So something that came up is you guys have a radiant cooled slab in a hot, humid environment. How do you guys manage condensation risk?
Yeah, it's just like they just put on their swimming suits and just slide across the floor, soap it up.
Is there a collection system in that space between the under slab and the upper slab where it is? It just like drips in there and it's like a kiddie pool. It's like a waiting section.
Slip and slide on the ADA ramps.
One thing I got to say about this building, we have integrated automation, so you can review it remotely, kind of live. I could probably get that website up now, but it's so controlled and then monitored that the system would basically just shut off if it was getting to the threat of condensation. So we don't have a condensation problem. The only time we really ever had condensation was when the building was wide open and we were testing systems, and there was no skin on the wall. You know?
That's the interesting thing about the building. It's so tightly controlled in such a narrow band. Between it, they've got energy recovery units and all that would help with any excessive humidity, but it's so sensitive to change that all the windows that are operable are motorized. And the reason they're motorized is that if you got a window in your office and like you left for the day and you accidentally left your window open, you could destroy the climate in the building to the point where it would take like a week to get it back to normal because that building was that window was open all night. So everything is motorized so that if something's open after a certain amount of time, it shuts down to make sure that there's not too much humidity or outside air pollutants or anything coming in. It's a pretty wild system.
That really makes
level of control.
Oh, it's God, the controls package on the building. I mean, the building is, like I said, 46,000 square feet. So if this was a typical classroom building, the Johnson Controls package, even on Georgia Tech, where they have a fairly extensive control system to begin with, might have been $400,000. I want to say the controls on the building were like $800,000 or $900,000. It was literally more than double what it normally would have been.
That's good. At Penn State, we had a little room where they were testing a radiant system like that in our 5th-year thesis. And all we had was alarms on the windows. So it would shut the system off and it would alarm. But it really made the guy angry because he had to come fix it every time one of us would open a window in studio. So it's good that you have controls that close the windows and shut things down. That's fun. There have been a ton of questions about the toilets. Can you talk some more about the foam, the toilet, the composting,
If Jimmy was there, he'd run over and demonstrate, but he's unfortunately up in New York today. So
yeah. So
hang on, Jimmy. Somebody asked about that. I saw it pop up about that little recycled bench that we have in there. The old lab casework. And the reason that's there is we had to set up a testing area for the. There's a group that comes in and monitors the water and that kind of stuff in the building, and they needed a little lab bench. So it was like, well, instead of going out and buying a piece of lab furniture, we stole a piece from another project that was being
there was a
out.
building right across the street that had one. We just stole it from them.
Yeah.
That
you
was perfect.
salvaged it. You salvaged it, guys.
That's
it was actually perfect because the design team had an elevation that they wanted, and the Cherry Emerson building, catty corner across the street, had old lab casework that they were throwing away. And so I set up a tour and I went and I walked through the building, and there was one room where it had almost a perfect match of the detail they wanted. And so then we said, hey, can we take this? And they're like, sure, we're tearing it out in 3 weeks. Just come get it between now and then. So we did. The one thing that was a little bit, we did more work to it than that. So we actually took it out, sent it to ball ground, did work on it, and then brought it back. So we didn't just take it across the street, but that was a salvaged lab casework from campus. So this is the composting bins, and basically we at the time had 2 options: Phoenix or a Clivus Multrum. We have a Clivus Multrum system, and we have 6 of these bins. There's 3 here and then 3 on the back side. And if I go over here, there's this leachate tank. So each of these bins serve typically 1 urinal and 2 water closets. And it comes through the pipe. It really needs to be stacked. It cannot be more than a 45-degree angle. So perfect scenario would be kind of a straight down, but it can go up to a 45-degree angle. And of course, in this assembly, we try to do a little fun engineering where it'd be like, okay, this guy gets the first stall on level 1 and then the last stall on level 2 or whatever. And but so there's pine shavings that come up to here. The waste goes on it. Most of it ends up being liquid. A very little bit of it ends up being solid. And so there's a little pump as it flows down through the pine shavings. It pumps up through these blue pipes and over to these leachate tanks. And then these leachate tanks, they actually have a majority of the mass. They fill up after about a month or so. And we put through the wall here a valve. So there's a truck that we have the Georgia Tech has a contract with that can just park the truck on the street, put their hose to that valve, and then pump out the leachate right from the road. And then they do that. And then it may be years and years and years before they have to empty out the solid part of the compost. And so that's generally how it works. So our black water system, we really don't have one. It just gets exported. And in our case, the state of Georgia has a requirement that you can't use it back on site. It's got to go to a third-party vendor. So so far, the leachate is the example of that. And there's like a water treatment place in Cartersville that takes all the nitrates out of it, the fertilizers, and then the rest of its water goes into the water system.
Yeah, so funny story on the composting toilet tanks there. You know, like Jimmy said, there's only 2 companies that make these things, and as you can imagine, they're not a mass-produced item. Phoenix is the company that originally had priced the job, and they were more of a vertical tank. They didn't take up as much floor space, so that's kind of what we designed around because it made for a smaller room. Well, somehow along the way, they realized that they were now basically the only one that could fit the room. And mysteriously, their price for these 6 tanks jumped up about $200,000 between design phases. And they just kind of went, well, you know, that's what it is. But hey, we're the only ones that fit in your room. So well, guess what? The room just got bigger and you just lost a, $400,000, toilet project. And we put the now less expensive, but larger units in. And like I said, they lost the job.
Yeah, I've been very thrilled with Clavis Multrum. They're a East Coast, Northeast supplier, and I think they were. It was a good result.
Yeah, it worked out well at the end.
Currently, Georgia Tech has a contract with them to do to manage it. Every 6 months or so, they come in and we'll put some new pine shavings in and spread out and the compost. But so it's pretty easy for them. The one thing that's real interesting about it is that from the water closet, the pipe is essentially exhaust duct. It's pressurized, and then from here, so air will flow through the pipe, through the stainless steel exhaust, and then out through the roof to through an exhaust riser. And that actually is an impactful design change because if I'm in a regular building, I would never suggest a waterless urinal because I'm always going to say a 1/8 gallon urinal because that flow of water really helps, especially with the odor. But in this scenario, with the restrooms being pressurized under negative pressure, and kind of always being sucked out, the waterless urinals work great here. There's no odor problems. It's always under negative pressure. Of course, if that exhaust fan ever goes out, the building stinks up in about 10 minutes. But
that was what I was just going to ask you. Is the whole room under negative pressure? Does it have its own ventilation system? Like what's happening in here? So that was really neat.
Yeah.
So what's up with the foam?
The foam is on the back of the toilets. And as you walk into the room, there's a sensor, and then it engages the phone with that tablespoon of water. And you just kind of hear it go, and then 30 seconds later, it fills up the bowl, kind of like from the sides down. And then the instructions on the wall say, please wait until it's fully foamed, and that's it. And so that is a consumable. Every month or so, they have to go and get that foam pack, and it's just like say like a soap dispenser type deal. It's about that big, and they put it in the back of the toilet. So the back of the toilet, instead of it being filled with water, it's just kind of a mechanism for that foam compartment.
Helps it slide down the
Got it.
the pipes.
Lubrication.
Yes.
But
Got it.
is there special toilet paper that they have to use in these, right? So some certain septic tanks and septic systems, you know,
There
is
is
any...
no toilet paper. It's the 3 shells on the back of the tank.
All right.
You know,
All
they use the
right.
3 shells, right?
And they thought we couldn't talk about toilets for an hour and a half.
The Fifth Element.
So
reference.
no, it is just kind of regular toilet paper. Yeah, I wouldn't say it's like super fancy and thick or anything, but it's nice. It's fine. Were incident, you know, you want to throw, you know, other things in the compost. So unfortunately, a lot of people have the habit of like going to get the paper towels and then putting it around the bowl and then throwing it all in the bowl. That really messes it up. And so that, you know, they were running into that in the beginning, and then of course it would clog up the pipe, and so anyways, that's what the signs are for. Hey, don't do that, you know, that kind of thing.
Not to belabor the waste system, but why couldn't the leachate be sent to the sanitary sewer system, municipal sewer?
Yeah, that would be against the Living Building Challenge.
Yeah, there is a valve, Ben, because there's the other system that we were talking about earlier that, you know, that kind of circulates some of the water around on the site there to, you know, kind of re-infiltrate it. There is a safety valve in there so that if something happened and that system got messed up, you can kind of flip that valve and temporarily dump to the municipal, but normally nothing leaves that site other than
Yeah.
A fail safe. Yeah.
In our case, that would not be the composting. That'd be everything else. All
Yes.
the sinks, the shower, the water cooler drain, the floor drains. That goes into that outdoor gray water tank that gets pumped up. And for that measurement period for the 1 year, we had a meter and it pumped it all up to the wetland. If we had turned on the city pump, that's where we could pump it to the city sanitary. Then we would have had to, you know, start over our 12-month measurement period again.
We have a question that's after this project, what were the biggest challenges? What were the surprise wins or the expensive mistakes? And what, after doing this, are you taking on to other projects or to inform your work on other projects? Now that's a very big set of questions, but I think you kind of get the theme.
I think the biggest win is the timber construction and the salvage piece. Of course, I'm a little bit, because of that nonprofit that I helped start, I'm real excited about how this building furthers the mission of salvage materials. And I think in 50 years, you'll look into this building and see the use of this salvaged wood and be like, wow. So I think that was a huge win. And then there's some real no-brainer, like embodied carbon pieces of it. You know, we're at this climate change deal. We're trying to calculate embodied carbon and figure it all out. And timber is definitely a big answer to that. And like, here we are in the state of Georgia, which has a huge pine industry, and none of it that cares about really too much about the buildings. And so I think now they do, and they're getting it, and they're all over it. But there's a huge potential for, you know, hybrid structures that include some timber in Georgia, for example, and anywhere else where they grow trees. So I think that's
Right.
that one. The biggest bad one, we had, you know, I gotta pick on the exterior shutters. If you go to the over here, there's these windows in the office space on both the east side and the west side. Of the east side, it's level 1 and 2, and on the I wonder if they let us in the office. They might not let us in the office. Anyways, these windows, there's an exterior Venetian essentially blind that goes up and down, And so the sun is blocked on the outside of the building to prevent the heat gain. And they really were, they're just kind of a afterthought. And we actually got them up and running and they're functioning now. So I don't want to trash talk them too much, but they were just a whole lot of a hassle. And the other thing that this eastern side in particular, Georgia Tech has these mature trees that they'll plant. And before the building started, they weren't there. And they were like, oh, well, we'll do these exterior shutters on the east side. And then in like 15 years, when they plant the trees, we won't need them anymore. Well, then Georgia Tech planted trees that were totally adult and 40 foot tall. So we kind of didn't need them from day one. So if I had to do that over again, we have them on the western side along here where the sunset really comes over this new park. I would keep them here and get rid of them on the east side. They were just kind of too much on the east side. And the facade on the east side wasn't really designed to deal with them. And so we eventually figured it out. But the facade on this lower level on the west side was designed for them. So I would say that would be my biggest kind of next project. For other projects, I do stuff like this. I am currently consulting on other living building challenge type projects. And also development, fundraising, whatever it takes. It's all interesting stuff. This is more about career aspiration, tough of the long term. I do think it's really important to innovate within sustainability in the industry. I think it's a differentiator. It's hard to win new work, and that's a way to do it. And so it has helped us with other clients, but it's just really fun, challenging work, and to figure it all out.
If I had to say what the biggest challenge on this project was, honestly, I think it was the budget. I mean, it sounds like $500 a square foot is you should be able to build anything for $500 a foot. But I think if we knew what it was going to take to meet all of these requirements in an actual functioning building like this, we probably would have told them earlier that it's going to take more money to do this. I mean, obviously we got it done, but it would have been far easier and maybe required, not that we sacrificed a whole lot of program or scope or anything. It would have been easier to do if we had $21 million to work with instead of 19. I mean, that's kind of always the case, but especially in this case where you've got so many oddities to work with.
You think that changes though moving forward? Like from the lessons you've learned from doing this one, do you think it gets easier on the next one, or is it just that each one is so individually different?
I think
it requires more.
Yeah, I mean, there's definitely going to be different, because each architect's going to interpret the petals a little bit differently and look to do different things and kind of push the envelope a little bit. But even just like the stuff that we've gone through already with the red list, knowing that, like, for example, I said that those roof drains are going to need a different washer and things like that. All that is done the same way when LEED first came out. Every manufacturer panicked. They were like, oh my God, I got to provide all this extra information and these sheets and this stuff and so on. And now it's just commonplace. Every submittal you get has all the LEED requirements already provided without you even asking for them. So that kind of stuff gets easier, but they're still challenging projects.
So I would say, I want to add to that. We had a great team on this. Everybody's bought in, and there was no doubt. And so when we came together, and the design team, the structural engineer, and the mechanical engineer, all these great firms, LAS, Newcomb and Boyd, Skanska, our subcontractors, man, we picked passionate subcontractors as well.
Yeah, it's funny. A lot of the subcontractors say, they say, we'll never do another one of those buildings. That thing was such a pain. There was so much effort, blah, blah, blah. And yet every one of them uses the pictures from the building in their marketing material.
I was going to say, it'd be really interesting to see, what you say dollars per square foot in construction, but it would be so interesting to see like how much of that, dollar per square foot number, if you rationalized out in your design team and everything. Like, it's great to hear that you had an amazing team, but like, how many hours did you spend researching just the red list? And that's after several buildings have already been built, right? So you had a
Mhm.
little bit to work with, but not everything. Like it'll get easier, which is awesome. But there's a lot of legwork to get to the point where you could build something. And then of course you said, on site you had these shutters and you had to kind of figure it out in the field. So, even
Oh, yeah, I
even
mean,
then everything wasn't.
our on-site management team was probably what 50% to 100% larger than it would have been if this was just a conventional 45,000 square foot classroom. That probably would have been a 2-person or 3-person staff. And what do you have out there, Jimmy? 6, 7 people out there
Yeah,
just to run down all the information.
I really kind of view that was the labor of love. That was kind of the gift of the project, is all that research and stuff.
Yeah, Jimmy worked for free for 2 years because he loved it so much.
I took a pay cut. Yeah.
With that, I'm always the bearer of bad news. Like it's 3 minutes till the end of the show, so I'd love to hear from both of you. What your final takeaway was, either on the building or what you learned or what you do again, or really anything around this case study. Like what's your takeaway from this project?
Is there a future for Living Building Challenge?
I think there's a huge future for Living Building Challenge. It's probably more so now as people have proven that these kind of projects can be done. As far as what I take away from it, if somebody came to me with another one of these, it would be expand that planning and upfront period. Because somebody had asked the question earlier, was this a design bid build project or a design build project or what? This was a CM at risk project, so we were selected to build it very early in the process, probably even before the schematic design started, back when it was just napkin sketches. And even with that, early involvement, if that process was 3 to 6 months longer, just to vet a lot about this out, it would have been a lot easier on the back end.
Yeah, I think there's a definite future. I think it's so clear and easy. My kids, 7 and 10, understand the building can generate more electricity than it uses. They can't understand much anything else along code. And I think the other thing is that when you're bought in and you're saying you're going to do it, we got to change that paradigm. Right in the past, it was like, oh, can I justify doing this? Why don't you go away and spend a month analyzing this LED light and tell me whether or not it's justified? Hey guys, give me a second. And now it's like
7 and 10-year-olds.
If we do a Living Building Challenge and we're all in and we don't spend that month worrying about whether or not our LED lights are going to save us any money, then it costs less to just do it. And so it just becomes a requirement and a no-brainer. So yeah, I think it's a very clear path forward, and should be a part of our considering our infrastructure in the future.
I think this is Georgia Tech is a perfect spot. These educational buildings is the perfect spot to for people to have a lot of access to it. So I'm going to end it with one final question that came up, which was, is this open to the public, and can people go and see it, or can they only walk through it on Google Maps?
Yeah, it's a public building. It's a campus building. You can usually just go during class times, like 8 to 5, Monday through Friday. Go check it out.
Awesome. There you go. People in the audience, you can go and check it out. We didn't get through even 10% of the questions that got asked on here. So
we're here if you want to keep it going. I don't know. I mean, Jimmy's kids sound like they're ready to go swimming or something. But,
I was gonna say we'll probably shut it down.
7:30, and they got home right at 7:30. So
yeah, I was gonna say we'll probably shut down the recording, but we will encourage people to pop over to Green Building Advisor. Kylie will write a blog post about this. We will try to populate some of the questions that got asked in that, and if you guys don't mind answering some of those questions, or people can continue to go and ask questions over there, we'll continue the discussion on Green Building Advisor. Thank you so much for your time
just
tonight.
Send us a link to where to look for that, Emily.
Absolutely. I will do that.
Jimmy, Bob, thank you guys.
You got it, man.
Good night, everybody.
Thanks, guys.
Good night.
bye, guys. Bye.